make sense or you want to see how the details fit together, then you can read my notes. All right?
Free license to just be on our phones the whole time?
I guess so. It's okay. I teach university. I'm used to talking to people who are on their phones all the time. Wow. The clocks are all slow here. Yeah.
Hello everyone, welcome back. It's my great pleasure to introduce Charlie Frohman, who will lead us to the quantum world, hopefully.
All right. Thanks. So there are lecture notes. They cover way too much ground. And you can find them by just following those directions on the board. And then you can look at those notes, and they'll be more in depth. But what I'm going to try to do is, in each 45-minute segment, sort of try to hit 3 big points and take my time to explain them. So Skein algebras are a K-theoretic approach to character rings. Okay, that's what they are. And so you have this formal object that is built out of equivalence classes of things that have to do with characters. And the one that we're going to be looking at is the Kaufman Brackett Skein algebra. And it has to do with SL2C character varieties. And what we're going to see is that to a point on the character variety, you get a collection of matrices. And those matrices tell you about the local geometry of the character variety. And then you can do computations with those matrices. And there are 2 lectures. In the first lecture, I'm just going to talk about the Kaufman Brackett Skein algebra and its relationship to SL2C characters. That's for the first 45 minutes. The second 45 minutes, I'm just going to talk about representations of associative algebras so that you can see that there is a correspondence between points on the character variety and irreducible representations of the Skein algebra. In the second set of lectures, they'll be more concrete. I'll show you how to embed the Skein algebra of a torus into the non-commutative torus, and then the non-commutative torus, you can describe irreducible representations of that very simply, and I'll use that to produce irreducible representations of the Skein algebra of the torus. And the second part of the lecture, I will actually calculate invariance of elements of the mapping class group of the torus using those representations. And that's the whole lecture. So let's get started. So what do I mean by a framed link? And that's an embedding of a disjoint collection of annuli into an oriented three-manifold. Okay? And they'll have a preferred side. So you're going to put a check mark on one side of the annulus, or choose a normal vector, but you want to have a preferred side for the annulus. So they have a preferred side. And you consider them up to isotopy. Okay, so two are equivalent if you can isotope one to the other. And the empty set is a framed link. So then what you do, given M, you let L of M be the equivalence classes of framed links. And now you choose Q, a non-zero complex number, and you take the vector space whose basis is the equivalence classes of framed links, and then you mod out by a subvector space spanned by the Kaufman-Brackett Skein relations. So when I draw a framed link, I'm not going to draw the whole annulus. What you're supposed to imagine is it's like that. And you have the preferred side up. And the reason why you have the preferred side up is we're going to cut and paste these things. And if one was the preferred side and the other was the unpreferred side, when you cut and pasted them, you'd get a Möbius band instead of an annulus. And that's the whole reason why you want to have a preferred side, because we don't want to work with Möbius bands. But here we go, minus, you ready, Q. And now the trick is you put your hand over the overcrossing, like this, and you sweep counterclockwise. And that is the positive smoothing. So you see, as I sweep counterclockwise, it picks out this region here, and so I smooth positively. And then I smooth negatively the other way. And that's the Kaufman-Brackett Skein relation. What you should think of is in K theory, that's like an extension. And then these are the two pieces. And so the extension, you're sort of abelianizing the category with that. But it turns out that it has other meaning. And now this means zero framed unlink with more link here. And I'm going to screw it up. You can turn an unlink just into a complex number. And so you take that quotient, and that is the Kaufman-Brackett Skein module of that three-manifold M. Okay. Yes?
You require Q squared plus Q negative 2.
No. Just, there it is. That'll be a degenerate case, because that'll mean Q is like an 8th root of unity, right? Okay. Okay, if you see an unlink, you can just turn it into a coefficient. So you have this is a link, and then somewhere there's an unknotted circle. You can delete the unknotted circle from the link and multiply by that number, which actually, when you put it on the other side, is minus, and that's more or less minus 2 if in some. Okay. Yeah, that's exactly right. The empty set will turn out to be the unit. So now if M is a surface crossed with an interval, it becomes an algebra under stacking. So what I want you to imagine here is this is a torus, S1 cross S1, but then I've fattened it up. And now here is a meridian of the torus, and you really can't see the back side. You shouldn't even. And now I'm going to multiply that, say, times the longitude. And the product is then this figure. But you see, I do have this little crossing ball here, and I can resolve it. And that's the positive. So I get a Q. And now it goes like this, plus Q inverse. And now I'm going to smooth it the other way, like that. And a basis for KQ of F. And now what we do is we suppress the cylinder, because the algebra structure depends on the surface. I could have, the pair of pants cross an interval and the punctured torus cross an interval are homeomorphic, but you get different algebras from the product structures. And so what you do is you just say what the underlying surface is. A basis for this is all multi-curves on the surface, including the empty multi-curve. Now, the mapping class group acts on KQ of F as automorphisms. So the automorphisms of the Kaufman-Brackett Skein algebra are in fact the mapping class group of the surface. And the way that is if I have a homeomorphism phi from F to F, then I can extend it to a homeomorphism from the cylinder over the surface to the cylinder over the surface by just letting phi hat of xt be phi of xt. And it clearly preserves the algebra structure. And right there, since you know that the Thurston compactification of Teichmuller space has the multi-curves as a dense subset, it has to have something to do with SL2C or SL2R. Okay.
So this is non-Abelian order.
Yeah, it's a non-commutative ring. Yeah, I know. And so the second I saw that, I knew it was about SL2C. So let's see what happens when we set Q equal to -1. Okay? Here we go. So here's the Skein relation. That's the positive. So I get negative that minus that. Now I'm going to rotate it 90 degrees and resolve again, and now I get this minus that. But because addition is commutative, they're equal. And so when Q equals -1, crossings don't count, framing doesn't count. Okay? And now that means that K-1 of F is a commutative algebra. Okay? All right. So let's try to get to SL2C. Suppose I have a matrix that's in SL2C. And I want to understand what its characteristic polynomial is. Well, that's the determinant, and we'll call the matrix A. That's the determinant of A, B, C, D minus lambda times the identity, which is A minus lambda, D minus lambda minus BC, which is lambda squared minus A plus D lambda plus, well, the determinant's 1, so that. And of course, that's the characteristic equation. And now the Cayley-Hamilton identity says that the matrix satisfies the characteristic equation. By the way, that is just the trace of A. And so what I have is A squared minus the trace of A times A plus the identity matrix is the 0 matrix. Well, that's well and good, but I don't like the fact that it's quadratic. And so I'm going to multiply through by A inverse. And so that's A minus the trace of A times the identity plus the trace of A inverse, plus A inverse equals the 0 matrix. So because it was quadratic, I really should have two variables running around. And what I'm doing is I'm polarizing the identity. In polarization, you take a polynomial of degree n and you turn it into a multivariable function in n variables. So I'm going to multiply through by another matrix. AB minus the trace of A, B plus A inverse B. And finally, I'd like to work in the world of functions, not matrices. And so I'm going to take the trace, and remember the trace is linear. And so I get, this functional identity for the trace of 2 by 2 matrices of determinant 1. And now what I'm going to tell you is that's the Kaufman-Brackett Skein relation. Okay. Yes?
Does it matter which, I mean, so here it's really you have an annulus, right?
Right.
So does it matter whether which like when you choose the other side to be the preferred side, this?
No, because it's the preferred side is a joke in the following sense, that if I put the check on the other side, think about it, I can always rotate an annulus and twist it over. And so all the preferred side is a bookkeeping system to make sure you're not producing Möbius bands when you cut and paste. That's all it is.
So after here, it doesn't matter.
Right, and it really doesn't matter. There's, because once you're on a surface, they're just diagrams on the surface, and then they're not annuli anymore because you're using the blackboard framing, and they're just curves.
Okay, so you don't allow framing, which twists around multiple times.
Oh, you do, but you can always, if it twists around multiple times, and remember, that's okay. So front, back, front, okay, and this one's, you can always relax this, and okay, I'm going like that, I'm going like that. I think if I relax it, it's like that, and you can always flatten them out. So you can always, you can always represent framing by the blackboard framing. You can always find a diagram whose blackboard framing is whatever framing you want. Okay, so we're going to think about a punctured torus, and we're going to think about the SL2C characters of a punctured torus and try to represent them diagrammatically. Now, the fundamental group of a once punctured torus is the free group on two generators. So there's a punctured torus. Okay. And now I'm going to put a crosscut there, and if I travel through that crosscut in that direction, it's the positive direction. And if I travel through that crosscut in that direction, it's the positive direction. I choose a base point that's away from there. And now the element of the free group, what I do is I take my loop, it's running around through, and that is, in fact, the loop. We'll call that A and that B. That is the loop AB. And so the fundamental group of that surface is isomorphic to the free group on two generators, A and B, right? They're the A is the loop that goes around here once and comes back. B is the loop that goes around here and one comes back. But then you can combinatorially just see them. And then by Seifert-Van Kampen theorem, if you're actually going to compute this, you would get those as generators. So there it is. And then it's really easy to write down representations of the free group on two generators. You just choose a 2x2 matrix with determinant 1 associated with each one of the variables. And so now the representations of pi 1 of that once punctured torus into SL2C are exactly SL2C cross SL2C, where you've chosen two matrices. And now to compute where a loop goes, what you do is you write down a matrix here and a matrix there. When you close up a loop, what you mean is take its trace. And if you have two different loops in a picture, then you're going to take the product of their traces. And now I'm going to draw a picture of the Cayley-Hamilton identity. All right? So the fully polarized Cayley-Hamilton identity for SL2C. Oh, yeah. This is, you should have a certification course. Okay. Here we go. So, boy, really? Wow. Okay. So first, I want to take the trace of A times the trace of B. And then that's going to be equal to the trace of AB, A, B, plus the trace of AB inverse. So A forwards, B backwards. There it is. Say it again? Oh, I put it on the other side. You see, I put trace of AB, A times trace of B on the other side. And so once I do that, I'll fix it. I'll fix it in a moment. Well, there you read a bunch of physics papers. And closing a loop corresponds to contraction, and contraction is taking the trace. So when you draw one of these diagrams, you're really drawing a picture of a tensor. And then each one of the free ends is a variable in the tensor. And then when you're gluing them together, you're contracting that variable out. So, but this is the amazing thing, okay? These diagrams are identical except for those 3 spots. Okay, and now there's a weird thing going on with signs. And to deal with the weird thing going on with signs, a closed loop has to be negative the trace. And so what you do is you define a eta of gamma, where gamma is an element of pi 1 of your manifold, to be something that when you evaluate it on a representation is negative the trace of rho of gamma. And that sign change, now really this should have been, and this was Jeffrey's remark, now this is no longer, once I make that interpretation, I use negative the traces. You see, because there are 2 of them, negative times a negative is a positive, and then those guys end up over there. And that is exactly the Kaufman-Brackett Skein relation. That is the Kaufman-Brackett Skein relation at Q equal to -1. So in the late 1970s, Claudio Procesi solved the first and second fundamental theorems of classical invariant theory for A-type Lie groups. And his answer was that the ring of invariance for the free group on n generators is spanned by monomials which are the products of the traces of freely reduced words. And then the second part of the theorem, the second fundamental theorem of classical invariant theory, says that all relations between those monomials are a consequence of functional evaluation of the fully polarized Cayley-Hamilton identity. Okay? And applying a Skein relation is functional evaluation of the fully polarized Cayley-Hamilton identity. And that's why the Skein algebra recovers the SL2C characters. Now, for an arbitrary 3-manifold, it doesn't quite, and that's because its fundamental group isn't free. And when you're calculating in that situation, you can see that the added relations come from handle slides along handles. And the actual ring has nilpotence in it. And then there's a theorem of Lubotsky and Majid that says if you have Andrews-Curtis, equivalent presentations of a group and you do that construction, you get the same ring. And so what this ring is an invariant of the presentation of the fundamental group of the 3-manifold that comes from its description in terms of handles. Okay. It is the unreduced coordinate ring of the affine scheme of SL2C characters of the fundamental group of whatever your 3-manifold is. That's what it is. All right. Wow. And I'm on time. So the next part of the story, this is due to Bonahan and Wong. And now zeta is going to be 2nth root of unity, where n is odd. Okay. And then what Francis and Helen did was they proved that the Kaufman-Brackett Skein algebra of a surface at that root of unity is essentially the Fock-Chekhov quantization of Teichmuller space. Okay? That's what they did. And along the way, they mostly identified the center. And they came up with this amazing trick. And I wanted to get rolling on this amazing idea. I want to talk about the Chebyshev polynomials of the first kind. Now, this is something that's always of the second kind. This is something that's always bothered me. The Chebyshev polynomials of the first kind are denoted S. And then they satisfy this. Okay, that's the first kind. Well, oh, you're right. It is the second kind. But why does it start with 1? Okay, this is the part that I just can't get my head around. Okay, and the first kind, of course, they start with 2. Okay, but then after that, it's the same story. Why would you do that? But so what these are associated with, of course, are trigonometric functions. And the point about the Chebyshev polynomials of the first kind is if you put 2 cosine theta in, you get 2 cosine k theta out. That's what they're doing. It's the power formula for the cosine. Or I'm going to write it like this. That's what they do. They also satisfy a couple of amazing identities. One is that they're closed under composition. So if I take tk of tl of x, I get tk times l of x. And if I multiply tk of x times tl of x, I get tk plus l of x plus t of the absolute value of k minus l of x. So this is the product of sum formula for the cosines. Okay? That's all it is. Now, given a framed link, it's an annulus, and you can use the annulus as a guide. And so, by the way, T3 of x is x cubed minus 3x, right? I gave you the definitions. You can. And what I want to do is I want to show you what I mean by threading a framed link by a Chebyshev polynomial. And it's a multilinear operation, so you do this for each component separately, and so you're going to get a whole lot of terms. But I'm just going to do it for one component. And I'm going to take this, and I'm going to take T3 of this, so you could know what I mean. Wish me luck. So there's x cubed minus 3 times x. That's what you mean by threading. And now, what I can do is there's a map. I'll call it tau k from the vector space of isotopy classes of framed links on the manifold to framed links on the manifold. Given a framed link, what you do is you thread every single component with tk of x, and that's the map. And, boy, here is their theorem. So zeta, primitive 2nth root of unity, then threading by the nth Chebyshev polynomial of the first kind descends to a map from k negative 1 of m into k zeta of m. So what happens is you take the image guys here and they satisfy the Kaufman-Brackett Skein relations as if the variable was negative 1. And furthermore, if you do have a component threaded with n and any other component, crossings no longer matter. Okay, and that's a theorem of Helen and Francis. It's a really tough theorem. So the way they proved it was by doing computations in quantum Teichmuller theory, and then Tong Lei then went back through it and came up with a direct proof that didn't mention it. And you can find that there on the web. So what that means is for a surface, you have a map from k negative 1 of the surface, which is, of course, the ring of SL2C characters of the surface. That's the ring of SL2C characters into the center of k zeta of f. And that map's injective. And in fact, z of k, boy, these are just terrible zetas. Does the board make noises for everybody besides me too? Or is that just me? Okay. This is tau n k negative f, and then what you have to do is adjoin peripheral loops. And the full center is, in fact, the characters along with, yes?
Where around F? What is it?
A surface. Finite type. It has to be finite type. Okay. Given a finite type surface. That means this is the peripheral loops. So what happens is, like if you have a puncture, there's a unique simple closed curve that bounds a punctured disk around the puncture, and you have to throw those in because they're not threaded, and yet they commute with everything because they don't have any crossings with anything else.
But you're not assuming that it's a free group.
No, and if, by the way, if it's a closed surface, this is the empty set. But that's the, and this is a theorem of myself, Joanna Kanya Bardashinska, and Tong Lei. Okay, so that characterizes the center of the algebra. What? Yeah, this is in fact the, well, this is a polynomial. You know, you should think polynomial, adding polynomials. This is a finite extension, and the degree of the extension is n raised to the number of punctures. Okay, so, but no, things aren't free. Okay, and that's a problem. So then, an algebra is affine if it's a quotient of a polynomial algebra or if it's finitely generated. And in the non-commutative case, what that means is that it's, in fact, finitely generated. And this was first proved by a student of mine back in the 90s, Bullock, that no matter what the variable, KQ of F is affine. Okay? And then with a graduate student, recently we proved that K zeta of F has finite rank, and also gave examples where it wasn't free, as a module over the center K zeta of F. And then the Artin-Tate lemma says that if your algebra is affine and it has finite rank over the center, that tells you that K zeta of F is affine. And so, in fact, the center of the Kaufman-Brackett Skein algebra is the coordinate ring of an algebraic variety. And that algebraic variety is a branched cover of the character variety of the underlying surface. So if you have a point in the character variety, there are finitely pieces of data you need to throw onto that to pick out a point of this variety. And this is, we call this the variety of shadows because Helen and Francis worked out what the data was to specify what it, and they called the data the shadow. Okay. Yeah, so I'm threading everything in the SL2C characters of F represented diagrammatically with the n Chebyshev polynomial. And that's a subring. And then I'm adjoining the peripheral loops to that subring. So it's a K.
So when you say K minus 1 of F equals X of F, you mean it's like the coordinate ring?
Yes, it's the coordinate ring of the, yeah, so maybe I should call C. How about this? This will make you feel better. That better? All right, that's what it is. Okay. So the next fact, which is due to Shatitsky and Shikora, is that KQ of F has no zero divisors. And you know, you're looking at this stuff, and it seems to you like it's from outer space because you're a topologist, and I'm telling you all these things about algebra. But think about it. The elements of this algebra are defined by diagrams. And the diagrams are multi-curves on surfaces. And the way you prove things about the Kaufman-Brackett Skein algebra is like with Dane-Thurston coordinates and train tracks and ideal triangulations. So when you actually read this stuff, it's very, very familiar. The goal is just a little bit different than what you, okay? And in fact, so this was actually first proved with punctures by Greg Muller. And then at the K, for Q equal to -1, this was proved by Charles and Marche. And then the fact that it has no zero divisors in general was then proved by Shatitsky and Shikora, and it's going to appear in the transactions, but it hasn't yet. It's that recent. So, because it has no zero divisors, its center is an integral domain, and that means if I take the center, and I don't even have to do the center because of K zeta of F minus 0, that's a multiplicatively closed subset. And now what I can do is I can localize K zeta of F. And that now is an algebra over the function field, you know, of the variety of shadows. like this. And its dimension is n raised to the negative 3 times the Euler characteristic of f plus the number of punctures as a vector space. And that's a theorem of myself and Kanya Bartoshinska. But more than that, this is a division algebra. And there's something mysterious about the Kaufman-Brackett-Skein algebra. It's a quantization, but it seems to not, and it clearly acts like a geometric quantization, but it doesn't really care at all about the underlying conformal structure of the surface. And it makes you believe that there's a global definition of the Skein algebra. And I would conjecture, you see, the commutant of an irreducible representation when you're working over a field that isn't algebraically closed is a division algebra. And so there's some way of realizing that the Kaufman-Brackett-Skein algebra is the commutant of some irreducible representation of the mapping class group. And that's probably what's really going on. And that's 45 minutes. So the next 45 minutes, what I'm going to do is talk about how you can wrap your head around irreducible representations of this algebra.
So let's take a 15 minutes.